Hello, everyone. Good morning, good afternoon, good evening, wherever you are. Welcome to the 28th session of the Global Ocean Oxygen Network webinar series. I'm Aileen Tan of the Center for Marine and Coastal Studies, CMAX, Universiti Sains Malaysia in Malaysia. I will be moderating today's webinar. The GO2NE Secretariat and I are very happy that you took the time to be with us and our excellent speakers today. Before starting, we would like to bring your attention to the Ocean Oxygen Organization website, where you can find links to the past webinar. So today we have two speakers today, which is Tom Hall from the Center for Environment, Fisheries and Aquaculture Science, CEFAS, United Kingdom, and also Monaliza Mohd-Din from Universiti Malaysia Terengganu. I will give you their short biodata later on. So before starting, we would like to bring your attention to the Ocean Oxygen Organization website, where you can find links to the past webinars and to the good news, the Ocean Deoxygenation newsletter. The QR codes on the screen will take you straight there. Let's move on to our session. We have two great scientists speaking today. Let me stop sharing. We will start with Tom Hall of the Center for Environment, Fisheries and Aquaculture Science, CEFAS, in the United Kingdom, and continue with Monaliza Mohd-Din from the Faculty of Science and Marine Environment, Universiti Malaysia Terengganu. Both speakers have just under 20 minutes to present, followed by about 10 minutes of Q&A. So if you have questions for our speakers at any time, you can enter this using the Q&A button at the bottom of the Zoom window. You can also use the chat button to share additional information or to reach out with the logistic problem. So let me take the time to introduce Tom Hall, a short biodata of Tom Hall. Tom Hall is a biogeochemical oceanographer and the principal investigator for autonomous monitoring at CEFAS. Tom has spent the last 15 years working with marine sensors, trying to get the most out of long-term instrument datasets. That includes hand-deployed buoys, landers, underway systems on ships, gliders, and surface vehicle. Most recently, Tom has been working within the UK government Blue Belt and Ocean Country Partnership programs to help partner countries develop their marine data collection and monitoring capability. Tom also manages the UK's wave monitoring network known as WaveNet. So without further delay, let me bring Tom forward to deliver his talk entitled Observing Ocean Oxygen in UK Shelf Sea. Over to you, Tom.
Thanks, Prof. Aileen. I'm Tom. I'm from CEFAS, which is an executive agency of the UK government. But I'm going to be showing a lot of the work I did during my secondment to the University of East Anglia. My work is mostly focused on getting the best possible observations to underpin our decision making, and this has increasingly meant sensors and autonomous platforms, things like this seabed lander we've got here on the left, and the kind of Slocum and sea gliders we've got here with Steve Woodward and Charlotte Williams from the National Oceanographic Centre. I think anyone who's ever attended any of these talks has probably seen this figure 100 times. Just in case, from our observations, it's estimated that global oxygen has lost 2% of its content over the last 50 years. Oxygen minimum zones have expanded. These are areas where concentrations are low enough to limit animal populations and impact nutrient cycling. But predicting deoxygenation is tough because of an incomplete understanding of what drives it and a lack of the data to parameterize and drive our models correctly. At the global scale, climate models have successfully estimated the change in oxygen concentration to within 10% of observed values, but they do tend to still underestimate variability and oxygen decline. So I'm going to talk about this from the perspective of the UK shelf, because that's what I'm most familiar with. In short, there's two areas which are most affected and most studied in this case. These are shown in these boxed off areas in white. We've got the central North Sea and this area just north of the Dogger Bank, and the central and the Celtic Sea over here. And unfortunately, I'm going to switch between both of these places quite a bit during the talk, just because that's where my data sets have come from and that's where my work has taken me. Just for a bit of context, this is a shallow shelf sea, so this area here is around about 50 to 80 meters, getting deeper as you head north, and this bit here is all under sort of 200 meters, down to around 70, I guess, where one of the buoy sites were. This map itself shows the areas vulnerable to oxygen deficiency. The reference is here. These are areas which we have data that show that for at least one daily value since 1998, there's been a oxygen measured below 6 milligrams per litre. So what we've seen at the moment is we do get oxygen deficiency in these areas. We have measurements and observations of it. Future climate predictions show it getting worse, and while the deeper areas suffering less, these particular areas being bad, and about a third of that is considered to be due to warming. The North Sea and Celtic Sea are areas which have a lot of anthropogenic stresses, particularly the North Sea. There's been hypoxic conditions have been observed since the 80s, which were primarily driven by excessive nutrient loads and riverine inputs. Since then, there's been a significant reduction in nutrients, especially phosphate, less so nitrate, but deficiency still occurs pretty regularly. And in general, primary production in the North Sea is declining due to warming, partly reduced nutrient inputs, as I said, but also changes in light climate. So we can, and I do, consider these systems with this oxygen mass balance I'm going to go through here, and this kind of puts into context the measurements that we're making. So the sort of southern part of the North Sea and northern part of the Celtic Sea and sort of coastal waters, here tidal and wind forcing is strong enough that they're always mixed. The whole water column is always in contact with the atmosphere on some short time scale. We have gas exchange between the sea surface here. We've got injection of bubbles. That's another flux that's probably won't get into in this talk. And then you've got the kind of combined effects of primary production and respiration. And then we've got seabed processes, which is mostly respiration, but other things as well. And then in the bits I'm going to talk about today, the stratified regions, these have a fairly sharp thermocline, picnicline. It's mostly temperature driven. So we have a section at the top that's still in contact with the atmosphere. We have a bit that's isolated from the atmosphere, the bottom mix layer. And here in the bottom mix layer, the only way it gets ventilated is advective or vertical through the thermocline. Entrainment as well. This is when if kinetic energy increases near the top, the thermocline deepens and you effectively move water from this area into this one, and effectively a flux. What is also a persistent feature of these regions is phytoplankton accumulate on the base of the thermocline. They're being fed gently with nutrients from the bottom mix layer, because the surface mix layer after the spring bloom is sort of completely depleted, and so they kind of accumulate on here, which means you can't see them with satellite. Right, so the general causes of oxygen decline in the North Sea and Celtic Sea are generally known, but the relative magnitude and net effects of these isn't. The warming certainly induces solubility, but how does the warming also affect biological processes is a bit less known. Stratification we've talked about before, which under climate change is expected to increase, but at the same time, climate change models also predict increased wind stress, so more kinetic energy going in, which might increase the depth of the surface layer, which means that do we get a shallower, a thinner bottom mix layer, which we'll come back to why that's important. Similarly, there's changes in circulation as well through climate change. Then nutrients, obviously, major input. So nutrients driving primary production, and actually I'll come back onto that a little bit later. Coastal waters are affected by nutrient inputs from rivers and runoff, and many climate models predict an increase in rainfall. And Met Office today literally announced that we've just had the wettest 18 months since records began in the UK. These regions that I'm talking about here are classed under OFSPAR as non-problem, these marine areas regarding nutrient input. However, they are affected by nutrients. And there are some lesser known potential factors as well, less talked about, the presence of microplastics or the construction of offshore infrastructure, which I'll touch on very, very briefly, just because I think they're interesting. It's important to note, though, that the stratification I was talking about before, it's only part of the problem. If what is actually driving it, and as pointed out by the paper cited here, is that it's the size of that bottom mix layer relative to the processes that are happening in it that actually causes deoxygenation. And as you compress that bottom mix layer, given the same fluxes happening at the seabed, the same processes happening at the seabed, you're effectively using up a smaller volume of oxygen. So briefly touch on those other drivers. So the way the plastics is believed to work, and these are all modeling studies, so we actually need observations to know if this is true or not, is that you reduce grazing pressure because the zooplankton are eating plastic instead. So in places where you're not nutrient limited, you would end up with a larger flux to the seabed of particulate organic matter. And then with the offshore wind farms, the models sort of suggest that, slightly counterintuitively to me, they would, the changes in wind stress mean that, and circulation mean that an increase in bottom deoxygenation. Right, back on actual data. So I was just talking about the North Sea mostly. I'm now switching to the Celtic Sea again. These are observations from the Celtic Sea on the right-hand side that show the kind of typical cycle that we get in these regions, where at the start of summer, things stratify. We usually get a spring bloom around this period, a lot of production. The red line is the surface measurements, the buoy, and the blue lines are from the seabed landers. So we have oxygen sort of cycling over, big spring bloom, and then sort of deteriorating, changing down as it warms up. So this is mostly thermally driven after the bloom. Gaps when instruments failed. And then towards the end of the year, really right at the end of the year, it remixes, where we now have a sort of fully mixed water column. What this means is that for most of the year, that bottom mix layer is completely isolated from the surface, and there's a kind of 3-month period where it's actually being ventilated. The models predict that this is going to last longer. And so we can imagine a scenario where it doesn't really take very long, where you really don't get much ventilation. It's also worse than that, because the amount of oxygen you start with at the beginning of the year when it stratifies is going to be a function of oxygen solubility. And so if the concentration is lower, you start with less oxygen, and then you're still using it up at the same rate, or maybe even a higher rate under a higher temperature regime. Well, it probably should be noticed why these lines are different. The blue lines aren't exactly temporarily spatially located with the buoy. They're all about 80 kilometers away from each other in different sediment types, because they were trying to assess a different question. But it's a particularly nice data set for showing this. This is important not just from the point of view of the communities in the bottom mix layer and productivity around these things. The shelf seas are a major component of ocean carbon cycling, and this effect of pumping particulate matter into that bottom mixed layer, but then also exporting a fraction of that into the deep ocean, is believed to be 20% of global anthropogenic CO2 is thought to be through this process if you extrapolate from the North Sea, which is the one that's been studied in particular. It's probably worth also mentioning as well, this kind of cycle, this annual cycle, isn't really in steady state. Some fraction of this organic matter stays there for long periods of time. It's not a case that the system kind of resets on an annual basis. Right. So actual direct observations from on the Celtic Sea again now. So this is, if we go back, we're just zooming in a little bit on this section here. We have on the right here, this is the vertical temperature structure based on the NEMO model. It's pretty good. I've sort of compared it with CTD profiles as best we could, and it's doing a reasonable job of reproducing what was going on, at least when we were there. So we're making the assumption that it was reasonably accurate the rest of the time. The green lines are boundaries for what I've defined as being the mixing layer. So we have a fully mixed surface bit, a transitional area, and then a bottom layer here. We kind of see it kind of changes in thickness and things and thins out a little bit towards the end. And this is oxygen as measured at the seabed. And what we see is it declines, as one might expect, and then it stops declining and starts increasing. And that's quite unusual and quite interesting and potentially unexpected. And the idea was to try and determine what was going on. So this lander was fitted with an ADCP, so we're measuring currents as well. And we did some work to try and figure out if this was a horizontal flux, was this movement of water horizontally across the bottom layer. So it's not really going up, we're just seeing oxygen that's been advected from somewhere else that's more ventilated. I'm going to show you a little bit more of that. Spoilers is no. Or maybe it's a vertical flux, maybe this is a flux across the thermocline. But if it was just increased cross thermocline flux, you'd expect to see the temperature going up in the bottom mixed layer as well, and we don't. Bastian's paper, he's in the chat, also has showed there's similar periods where we've had big spikes in vertical mixing, but these were seen to be quite short-term events based on storms or something passing through. Similarly, Charlotte's paper showed similar things. This is persistent over 15 or so days. So the other option is it's a change in the oxygen gradient. There's actually a balloon within the thermocline here, there's an increase in oxygen to the bottom mixed layer just because the concentration gradient has increased. But we don't have observations of that, unfortunately, and it can't be seen on the satellite, so we don't really have anything to corroborate it. If that is the case, I guess there's the argument that if that would have been driven by regenerative nutrients being put in rather than through the surface, so the net effect on oxygen in the bottom mixed layer might actually be zero, and this effectively, if at the end of the time series, at the end of the year, does it actually make a difference? I'm not sure. Interesting thing to look further into, but effectively this is as far as these observations will take us, because without knowing a bit more about what the vertical structure of oxygen was like, it's not possible to sort of answer this question. What I was able to show was that it wasn't advective. So these are probably the stupidest plots I've ever managed to get into a paper. But effectively, what we have with the ADCP was very circular tides in this region in the Celtic Sea. Effectively, the water tends to spiral around and not really move very far. So we have a tidal current and then a very, very small residual current. If you imagine there was a parcel of water on top of the land when it moves around, this is the track it would take. And effectively from that, we can determine when a parcel of water has kind of moved away and then come back again. And so we can compare the difference between what the concentration was when the parcel of water was over the lander and when it's come back and we've seen it a second time. And then taking this method a bit further, we've fitted a statistical model that would allow you to kind of determine this without having to have these little traces. But as a proof of concept, it worked quite well. And we were able to determine the oxygen consumption rates in the bottom mix layer at a few different sites based on this method. And they effectively showed that on top of being able to determine what the bottom mix layer rates are, we could show that it wasn't an advective flux because there wasn't any correlation between increasing oxygen and the movement of water. Okay. Next, I'm talking about a later project. This is now back on the North Sea, Alter Eco, which, yep. And here we managed to see, I'm going to back up very slightly. So Alter Eco was a pilot study to demonstrate if you can do long-term monitoring with autonomous vehicles like buoyancy gliders. I'm going to assume people know what buoyancy gliders, but ask a question later if you need to. There's various objectives, but one of them was to assess the local rates of oxygen production and consumption. What we found was that it's quite difficult trying to observe the same water mass over time. A lot of assumptions are often made about spatial heterogeneity, you know, how different things are over space and time. And what we found on this particular bit of the glider transect, so this is the glider traveling east to west as it moves east and then west again. And what we can see is there's this cold region about 60 kilometers long, which is, it's cold, it's slightly salty, it's very low in oxygen, it's also quite high in nutrients, and this has persisted right until mid to late November, and then eventually mixes down. So same sort of features that we saw in the Celtic Sea. But this isn't currently reproduced in models. They don't show this. It's also very, very shallow. It's very, very thin layer. So quite susceptible to deoxygenation. Yeah. What we also saw is quite sharp horizontal boundaries as well. So I think sometimes there's a bit of assumption that the bottom mix layer was quite homogeneous across this area. But what we found is that there are actually quite sharp fronts that separate different regions of bottom water. But one of the things we were trying to do back on the vertical mixing, the question we had from the Celtic Sea, and perhaps the largest unknown, was what are the rates of across the thermocline mixing. The best observations previously were these 3 days in 2009 from a lander and some deployed gear from a vessel from the Ravelli paper. This is just north of the Dogger Banks, pretty close to the Alter Eco site, and they found good measurements, but really variable, large uncertainties. And we know it's variable depending on topography and currents and wind. In autumn, we know, Julianne's in the chat as well, in the Celtic Sea, that vertical mixing supplies nutrients to phytoplankton at the base of the mixed layer, which promotes production, recycling of organic matter back into the mixed layer. So the net effect of all of these processes is still quite hard to see. So we, in addition to our normal gliders, we had a microstructure glider called Kelvin. It doesn't quite look like this. Effectively, it's got a big microstructure sensor stuck on the front. But this is directly measuring turbulence as it goes through the thermocline, in addition to measuring oxygen on its tail, which is perfect, right? 3 months of vertical fluxes, order of magnitude more measurements than before in this region. No, not quite that easy. The very shallow bottom mixed layer is actually really hard for these instruments to measure. The gliders need space to turn around. They need time to do so. The sensors need time to accurately measure. And we found that the trade-off between not crashing the glider into the seabed, but also it's spending long enough in the bottom mixed layer to measure it accurately was really fine sometimes. And gliders only really measure good data when they're flying correctly, as anyone who works with them probably knows that all too well. But worse on top of all that, the oxygen sensor on these gliders is sort of exactly in the wrong position. And in addition to the normal sensor response time that we deal with, they also have an issue of geometric lag in terms of parcels of water as it kind of flows past the glider gets stuck here. And this is what it affects like. So effectively, when we deployed our normal seabird rosette system, CTD, with the glider, you'd end up with the blue line, a nice kind of sharp, the down looks about the same as the up. The temperature on the uptode is severely lagged, so it doesn't really see the same parcel of water, and effectively it never really gets down to the true temperature, and then the oxygen is lagged on top of that because the oxygen sensors respond even slower than the temperature sensors. This is a bit of a challenge. It should be noted that actually with normal CTD casts, it would have been perfectly possible for people to miss this bottom mix layer by just not going quite close enough to the seabed. And if the weather is rough, you can understand why people wouldn't want to destroy their expensive CTD by smashing it into the seabed. But we did manage to develop a way of correcting for the lag effects and for being able to pull out what the overall oxygen gradient was, even if we couldn't completely reconstruct the vertical profile, by making some assumptions about the structure of the thermocline and temperature oxygen concentration. So we do now have a data set which Charlotte's published recently, where we have vertical mixing from just before the breakdown of stratification, where bottom mix layer oxygen concentrations are lowest, and it again persisting right into November. We see that mixing is still mostly driven by episodic events. We have a sort of baseline very low mixing rate and then little pulses of material being thrown in. I don't know how well the models actually reproduce that. So it does look like vertical mixing seems to alleviate oxygen decline in these regions. This is a process that needs to be factored in, but there's still sort of a larger question of is this only at certain times of the year? If there was more light, and vertical mixing would actually be supplying more nutrients back into the deep chlorophyll maximum, which would lead to more primary production, which would lead to a flux back to the seabed again and more respiration. So it's still not a kind of.
You have one more minute to go, Tom.
Oh, one more minute. Well, that's
yeah.
good because I've got one slide left.
All right,
okay.
Thank you.
So where we're going with all this is where we're trying to take all this is to see to the complex systems, and they behave differently in different inputs at different times of year. So we need more useful models. Here we have an example of what happens when you actually include the oxygen observations versus when you let the model just run on its own. We're working towards having underway systems where the data is directly fed into a model that is constantly running, so we can use it for testing hypotheses, testing management strategies. But there's a lot of work still needs to go. It reverts to its kind of baseline system as soon as you take the glider data away, so it doesn't really assimilate it properly. There's a load of new work going on to make making models which are easier to train, easier to adapt to more modern understandings of how the mechanisms work, how to include data better, and there's a nice way to go with that. And we can talk about this some other time if there's any questions, but fundamentally that's mitigations. Long-term observations are possible. Sustained observations are needed for building our better models, and we actually do need to observe some of the places. I didn't really touch on that enough. Whoops. Observations of lesser studied regions to test our assumptions. Thank you.
Okay, thank you, Tom. Thank you for your informative presentation. We have one question for you. What would be the ideal way of monitoring or observing these regions, in your opinion? And how much data is enough? How much is enough? You'll be, if I mean, at least the minimum. If not, there will be massive. We need your thoughts on that. Thank you.
Okay. I think the largest. That's the first bit. So that kind of goes in the same direction. The largest problem at the moment with a lot of these observations is kind of knowing how representative a particular point measurement is. If you do a single transect in a lot of these regions, you can come to conclusions about what the changes in space are, but actually they're temporal changes or vice versa. And so any kind of observation system needs to be able to take into account that, whether that means gliders flying in particular patterns, or my personal preference would be some sort of drifting glider that you supplement with other observations, so you put it in a bit more of spatial context. How much data is enough? When models reproduce features that we're interested in, I think it's getting there. It's a seeing the DeepMind paper, which has shown that they were able to effectively get similar accuracy to ECMWF's weather forecasting with a neural network based model for a fraction of the computational cost, at a fraction of the speed. I think it was 10,000 times faster. But effectively, it's able to more easily take historic data and combine it to make a better model that has a higher skill compared to the numerical model, where you have to have defined, okay, what's the relationship between these two different things. I think the problem with oxygen and biogeochemistry here is we don't have those training data sets.
Well, okay, thank you very much. Thank you, Tom, for sharing your insightful and because we are running out of time, so I have to let you go. And thank you. Stay tuned. There might towards the end, if you have extra time, we'll come back to you. Thank you. Thank you so much, Tom.
Quite as much. Thank you.
Thank you. So now let us move to our early career oceanography professional, ECOP, Dr. Monaliza Mohd-Din. Tom, can you stop sharing, please? Thank you. So Dr. Monaliza Mohd-Din is a lecturer at Universiti Malaysia Terengganu. Her research falls in the field of marine biology and ecology, focusing on marine phytoplankton, zooplankton community in response to issues such as sustainability, pollution, and ocean climate change. She has extended her research interests towards marine pollution, particularly related to water eutrophication and hypoxia environment for prediction, management, and mitigation of harmful algae bloom. So without further delay, I would like to invite Dr. Monaliza to take over the floor. Over to you, Dr. Monaliza.
Hi, thank you, Prof. Aileen. Okay, so hello for everyone, and good morning from and good evening from Malaysia. First of all, I would like to thank to the organizer for selecting me in this session today. And my name is Monaliza, and currently I am a lecturer at Universiti Malaysia Terengganu, Malaysia. And for today, I would like to share the findings of my study on prolonged high biomass bloom. High biomass diatom blooms induce the formations of hypoxic-anoxic zone in the inner parts of the Johor Strait. Okay, so for the several cases of the harmful alga blooms event have been reported in the Johor Strait, hence indicate that this strait high possibility to be an alga bloom hotspot in our water in Malaysia. So Johor Strait is located between the Malaysia and Singapore, and this strait serves as the agriculture area for this country. However, the uncontrolled coastal development and agriculture activity around the Johor Strait has increased water pollution and also eutrophication in the area. So the enrichments of nutrients, or known as the eutrophication in the water, will shift the alga community from high biomass diversity to one or more species that form harmful alga blooms in the water. So these high biomass blooms have a harmful effect that cause severe dissolved oxygen in water that eventually cause mortality to the aquatic life. Over the years, this Johor Strait has been developed intensively and has been utilized, including act as the important mariculture site for cage fish, for green culture farm, green mussel farm, and also port activity, land reclamation, and for the human settlement. The presence of the causeway that connecting between Malaysia and Singapore has divided the strait into two straits, Western Johor Strait and also Eastern Johor Strait respectively. The causeway act as the physical barrier at the inner parts of the Johor Strait and cause the blockage of the water flow, and also cause the poor flushing between western and eastern Johor Strait, and this lead to the eutrophication problems in that area. So for the occurrence of the harmful algal blooms in the Johor Strait were not new, and the incidence of the harmful algal blooms we can trace back to the 1890s and cause mass mortality to the aquaculture and also to the wild fish, to the shellfish, and lead to the damage in the mariculture industry both for Malaysia and Singapore. The unprecedented mass mortality of Hwai and also culture fish along the strait was reported in 2 years of 2014 and also 2015 due to blooms of the ichthyotoxics of Calodinium australe. However, after some fish kill incidents have been reported after 2016, but the causative species was not being clarified and remain unknown, partly due to the lack of the monitoring efforts. So, taking into account, the attempt has been made to clarify the high biomass bloom relating the hypoxia condition relating to the hypoxia condition along the inner parts of the Johor Strait, where we conducted 1-year field sampling between May 2018 and April 2019. The 5 stations was selected in the inner parts of the Johor Strait, and this effort also to continuously monitor the water quality and the occurrence of the harmful algal blooms in the Johor Strait. So the objective of this study is we want to investigate the prolonged high biomass diatom blooms that induce the formations of hypoxic and anoxic zone in the inner parts of the Johor Strait. And also we want to determine the parameter and nutrient that affecting the phenology of the algal community in the strait. Johor Strait were influenced by southwestern monsoon, dividing the years into main monsoon, the northeast monsoon, November to the March, and the southwest monsoon, May to September. The intern monsoon, or known as the transition period between the main two monsoon, happened on the April and October. So monthly rainfall average during the study period show that low between May and September. However, during the intermonsoon, the rainfall is higher, average up to 400 millimeter in October 2019. And then beside northeast monsoon also characterized by higher rainfall, and the average of the rainfall more than 300 millimeter in November to December during that time, and the rainfall gradually decreased from January to March. Okay, this rate also having semi-diurnal tidal cycle with the maximum tidal elevation can up to 3 meter during the high tide and less than 1 meter during the low tide. Okay, during the study period, the physical parameters such as dissolved oxygen, the temperature, the salinity, and were measured in situ at the different depth of the water, depend to the water depth. So we measure on the subsurface, 1 meter, 5 meter, and 8 meter depth. The stratifications of the water depth were observed as the dissolved oxygen were higher in the subsurface and decrease with the increasing depth. Supersaturation dissolved oxygen were also observed at the subsurface water for all sampling sites, and lowest oxygen were observed at 8 meter depth, especially at the station 3 and station 4. The water temperature decreased with the increasing of the water depth, but salinity were greater in the deeper depth. In this study, we found that the high productivity of the chlorophyll A range from 12 to 48 microgram per liter, with presence of the high biomass blooms of several diatoms were also observed in the inner parts of the Johor Strait. Most of the diatoms that contribute bloom in the Johor Strait were by Scatonema, Cataceres, Rhizosolinia, Thalassosira, and Eucampia at the different depths of and the different locations. Okay, so the temporal and spatial changes of nutrient and chlorophyll A were analyzed. So we found that concentrations of the nitrate, ammonia, and silicate were higher at the station 3. When the blooms of the Rhizosolinia took place in August 2018. After that, the blooms of the Scatonema took place at the station 2 and station 2 and station 3 with high abilities of the nitrate, ammonia, and silicate. At the same time, blooms of the Scripsilla also were observed at the station 4 with high concentrations of the phosphate. The highest level of the chlorophyll A during the blooms of the Scatonema at station 3 were coincided with high abundance of nitrate and also the abundance of the silicate. Lastly, in March 2019, high biomass blooms of the Thalassosira were observed in the western Johor Strait in station 2 and station 3, and the bloom collapsed after the silicate depletion. So we found that prolonged high biomass blooms of the Scatonema, Cataceres, Rhizosolinia, and Thalassosira were observed in the inner parts of the Johor Strait. And the alga blooms at the station 2 and station 3 were most contributed by the Rhizosolinia, followed by Scatonema, Eucampia, and also the Thalassosira throughout the years. Okay, meanwhile, at station 4 and station 5, we found that the blooms were dominated by the Scatonema, shifted by the warm blooms of the Scripsilla, and followed by the blooms of the Cataceres and also the Rhizosolinia. These high biomass diatom blooms were lasting at least 1 month, with dominated by the single species or co-dominated by more than single species throughout the study was conducted. During this study also, we found that a hypoxic-anoxic zone were observed in the inner parts of the Johor Strait with the DO concentration less than 2 mg per liter, covering of the area 10.3 km square. The station 3 and station 4, the station 3 and station 4 consistently experience hypoxia-anoxia throughout the study period. Beside the dissolved oxygen depletion less than 3 mg per liter, sometimes were observed at the station 2 and station 5 during the southwest monsoon and also during the northeast monsoon. However, the outer station, which is station 1, did not show any severe dissolved oxygen depletion during the study was conducted. Okay, so this animation that I using Ocean Data View show the monthly, spatial, and temporal of dissolved oxygen in the inner parts of the Johor Strait. And this contour map show the spatial distribution average of the dissolved oxygen in the inner parts of the Johor Strait between May 2018 to April 2019. At Station 3 and Station 4, high biomass blooms of the algae prohibited the vertical dissolved oxygen, dissolved oxygen exchange, and resulting the organic matters from the algae blooms deposited to the bottom water. So this decomposition process eventually used the dissolved oxygen at the bottom water and caused the severe depletions of the dissolved oxygen at 5 meters and below. Besides, the decomposition rates of the dead algae cell accelerated by the higher water temperature, especially during the southwest monsoon, thus exhausting the dissolved oxygen at this hypoxic zone at the S3 and S4 station. Also, the presence of the causeway in between the western and eastern Johor Strait caused the blockage of the water flow and poor flushing between the straits. Okay, so the long water residence time, poor flushing, and the water stagnation in the area enhance the bullards of the nutrient, and this promote the prolonged algae blooms in the inner parts of the Johor Strait. Okay. As a summary for my study, the occurrence of the prolonged high biomass data blooms of the Skeletonema, Cataceres, Rhizosolinia, and Thalassosira were observed lasting at least a month at the inner parts of the Johor Strait. Hypoxic to anoxic dead zone was identified in the inner of the Johor Strait, covering an area about 10.3 kilometers square. And this high biomass of the atoms bloom triggered by eutrophication in the area were the factor that induced the formations of the hypoxic-anoxic zone in the inner parts of Johor Strait. So another cases that relating hypoxia related fish kill in Malaysia, we can see the events has happened in the Malacca Strait, in Penang, Malacca Strait in 2019. So during this event, happened due to formations of the hypoxia during algae bloom due to algae bloom degradations. So during the event, massive fish kill was happened during that time. And as you can see, the oxygen level drops less than 2 milligrams per liter for the bottom water during that time. So the high biomass blooms of the diatoms, such as Cosnodiscus, Cataceres, caused the dissolved oxygen in the water column was very poor, with the lowest DO level were observed in the fish aquaculture area. At the surface, dissolved oxygen level were only 2 milligrams per liter, and the bottom water about 4 meter depth were less than 1 milligram per liter. So these blooms of the diatoms induced hypoxia, caused massive fish kill during that time. And the total loss was estimated by 50 tons of the catch fish and give huge damage to the aquaculture operators. So as a take-home message, okay, the impacts of the harmful algae blooms, impacts of the hypoxia to the aquaculture activities, to our socio-economy, to our food safety and security has been recognized as a global issue and required collaboration both by publics and also the government partners. Okay, so understanding the blooms of the dynamic existing that or emerging harmful algae blooms is important in order to provide more holistic harmful algae bloom management and monitoring programs. And also use of the advanced technology, especially in research area, will contribute in order to reduce the harmful algal bloom impact, promote sustainable development in our aquaculture industries. Okay, so this is my research paper that I studied previously, and that's bring us to the end. I would like to thank you for your time and your attention for this evening.
Thank you. Thank you, Monaliza. Thank you very much. So we have some questions in the chat box for you. The first one is from Rohil Arif. His question to you is, have there been any methods established to treat algae bloom in inner straits of Johor to help reduce the risk of hypoxia conditions?
Is there any? Sorry, Prof. Can you?
Sorry?
Sorry, can you repeat the question?
Have there been any methods established to treat the algae bloom in the inner straits of Johor to reduce the risk of hypoxia conditions? You can stop sharing so we can see your face. Yeah. Yes, good. Yes, do you want to answer that? Yeah.
The method they established in a parts of Johor to reduce the hypoxia, right?
Yes, to treat the algae bloom to reduce hypoxia.
Currently, we just doing the regular monitoring for the harmful algal blooms. And then to reduce the hypoxia condition in the inner strait. Eventually we need to control and to regulate the discharge of any water discharge into the Johor Strait. So the method for the properly to reduce the hypoxia in Johor Strait, I think still don't have. We just do the properly monitoring at the Johor Strait currently for the mitigations of the harmful algal bloom effects.
Okay, still very much depends on monitoring, right? Without okay, thank you. The next question is from Pascal Nahasi. He was asking, which techniques have you used to classify or detect those diatoms?
For this study, we use for technique using like microscope compound. But for this current study, we use for the metabacodine. The advanced study, we use for metabacodine to identify the atoms or another harmful algal blooms in our study site.
Okay. The next question for Grand Picture, he is asking, how much did OM from fish farms contribute to low oxygen?
How much the? Sorry,
how much did OM, it was stated here OM, I'm sorry, I do not know. Yeah, from fish farms contribute to low oxygen?
I think might be how much the nutrient waste maybe.
Okay.
Organic matter.
Organic matter. Okay. How much the organic matter from the fish farms contribute to low oxygen?
For the exactly data we don't have, but as we know, the current practice of the most aquaculture operator they just use the sometimes from the feeds of the fish, and then also the trash fish. So they just discharge into the water column without the proper treatments. Actually, for the data, how much the exactly amount they discharge the nutrient or the organic matter, we don't have.
Okay, one last question for you is there any study or device that can help prediction the occurrence of HABs to help or reduce loss, in fish or to prevent its occurrence?
The current study in HIB, for currently we use sensor. For the physical parameter, especially for the DO, and also we 1 meter is also 1 meter is like the normal monitoring. The monitoring, we go and we do the sampling about regularly every month, and then we put the logger to monitor the physical parameter, especially for the DO and the temperature. And then we also collaborated with the remote sensing for the monitoring of the chlorophyll A.
Based on the monitoring, can you come up with prediction, you know, of the HAB occurrence?
HAB occurrence.
Prediction, yeah.
Yeah, based on the monitoring, especially for the regular monitoring, we can predict because by the nutrient discharge, what the compositions of the nutrient discharge, we can predict what the species after that will blooms, and the successions of the species, the bloom will took place. Yeah.
Okay, thank you. I would like to bring Tom to the floor, to the highlight here. Tom, we have one question for you, Tom. Okay, on the video, yes, thank you very much. He was stated here. Thank you for you sharing your information and interesting result about the oxygen condition and observation of UK Shelf Sea. I wonder if the variability of oxygen minimum zone in the open ocean can influence the oxygen condition in the UK Shelf Sea.
It can and it does, but because there's a long residence time of water in the North Sea, it takes a long time for the water to come in and go through, and that tends to be, we tend to consider it kind of like a winter reset. So over winter, the nutrients come in through Felice, the Dogger Bank, come around Scotland and come in. Effectively, that's oxygenated water from being fully mixed and being brought up at the shelf. So it does. What we think might happen in other places though, so in sort of UK overseas territories, there's been a question of whether deep, low oxygen waters being upwelling around those locations, but we have even less data there to answer that question.
Okay, thank you. Is there any more questions that we need? I think, okay, there's one question here, most probably to Monaliza. How did you measure anoxic conditions? You know, if Tom wants to answer that also, because it did not direct to anyone. Tom or Monaliza?
For my research study, we measure with the multi-parameter. So at the different depth of the water column. So we take the using the multi-water parameter to get the data.
Okay, all right.
Because for the Johor Strait is about 10 or 15 the water depth.
All right, thank you very much. I think we have come to an end of this webinar. There's still a lot of questions pouring in. I guess for those who is still interested to link or to share the questions with our speakers, the Secretariat will capture all these questions and will share with the speakers and see how best we can actually response to all your questions. So thank you again to our speakers, Tom Howell and Monaliza, and to all of you for your participation today. We hope to see all of you again for our next webinar at the end of this month. And be sure to follow us via the below social media, which is stated in the QR code. In the meantime, you can find more information there and sign up for our current calls for information on activities for World Ocean Day in June 2024. So have a pleasant day or night wherever you are. Thank you very much for joining and supporting our webinar. Thank you very much and have a good day to all of you. Thank you. Thank you very much to Tom and Monaliza. Thank you very much to everyone. Thank you. Bye-bye.